For the last 25 weeks, we have not just been talking about solar panels, we have been learning electrical systems. That is a big difference, because solar is not one part. It is not just panels on a roof. It is not just a battery. It is not just an inverter. Solar is a complete power system. And if one part of that system is wrong, weak, undersized, or misunderstood, the whole system can give you trouble. So this week, week 26, we are going to step back and summarize the first 25 weeks, not as 25 separate lessons, but as one complete learning path. A lot of people start solar with the wrong first question. They ask, how many panels do I need? That is not a bad question, but it is not the first question. The better question is, what am I trying to power? For how long? Under what conditions? And how will the whole system handle it? That question changes everything, because now we are not guessing. We are designing. A solar system for a phone charger is not the same as a solar system for a refrigerator. A solar system for weekend camping is not the same as a solar system for full-time RV living. A solar system for lights and a fan is not the same as a system that needs to run air conditioning, microwaves, pumps, tools, or a whole house. The load decides the system, not the other way around. Early on, we focused on the basic language of solar and electricity. Volts, amps, watts, DC, AC, series, parallel. These are not just textbook words. They decide how the system actually behaves. Volts are electrical pressure. Amps are current flow. Watts are the work being done. DC is what solar panels and batteries use. AC is what most household loads use. Series increases voltage. Parallel increases capacity and current handling. Once you understand those basics, solar starts to make more sense. You stop just looking at parts. You start seeing relationships. That is when you can look at a system and understand why it works, why it struggles, or why it failed. Then we looked at solar panels. And one of the biggest lessons is this: the rating on the panel is not guaranteed all-day output. A 400-watt panel does not mean you get 400 watts all day long. Sun angle matters, heat matters, shading matters, clouds matter, panel direction matters, flat mount and tilted mount are not the same. Roof mount and ground mount are not the same. Even a small amount of shade can hurt production. And heat can reduce panel output. That is why real-world solar output is always different from the perfect number on the sticker. The sticker tells you what the panel can do under test conditions. The system has to work under real conditions. Then we moved into batteries. And this is where many people start to understand solar differently. The battery is not just a storage box. The battery is the heart of the system. Panels recharge the system, but the battery carries the hit. When a big load starts, like a microwave, pump, refrigerator compressor, air conditioner, or power tool, the battery and inverter have to carry that moment. Solar may help, but the battery bank is what keeps the system stable. That is why battery size matters. Battery type matters. State of charge matters. Depth of discharge matters. Charge settings matter. Battery connections matter. A weak battery bank can make a good inverter look bad. A poorly connected battery can make a system act like it is undersized, and a battery that looks fine at rest can fall flat under load. We also spent time on system voltage. 12-volt systems can work. 24-volt systems can work. 48-volt systems can work. But they do not behave the same. For the same amount of power, lower voltage means higher current. Higher current means larger wire. More heat. More voltage drop, more stress on connections, and less room for mistakes. That is why a 2,000-watt load on 12 volts is a very different animal than a 2,000-watt load on 48 volts. The watts may be the same, but the current is not. And current is where a lot of trouble starts. Loose connections, undersized wire, bad crimps, weak fuses, and poor layouts all show up when current gets high. One of the most important ideas we covered was the solar power chain, solar panels, charge controller, battery bank, inverter, loads. That chain matters because the visible problem is not always the real problem. An inverter alarm does not always mean the inverter is bad. A microwave shutting off does not always mean the microwave is bad. A charge controller acting strange does not always mean the charge controller is the problem. The real issue may be upstream. It may be a loose battery cable, a weak connection, a fuse holder, a breaker, a bus bar, a wire that is too small, a battery that cannot support the load, or a panel array that is not producing what you think it is producing. Good troubleshooting follows the energy path. Bad troubleshooting guesses and starts replacing parts. We also covered the difference between wiring diagrams and schematics. A wiring diagram shows where things connect. A schematic shows how the system works. Both are useful, but they do different jobs. Then we looked at wire sizing, fuses, breakers, crimps, connections, disconnects, and protection. These are not boring details. These are the parts that keep a system safe. A system can look clean and still be wrong. A system can work at idle and fail under load. A wire can be too small. A fuse can be in the wrong place. A breaker can be the wrong type. A crimp can look okay and still create heat. A loose connection can become the hottest point in the system. That is why we keep coming back to the same idea. Solar is electrical work. It needs to be respected. Then we moved into inverter and inverter charger systems. An inverter does not just make AC power. Some inverters also charge batteries. Some pass shore power through. Some support split phase 120, 240-volt power. Some blend multiple sources. Some are simple. Some are hybrid. Some are built for small loads. Some are built for serious off-grid or backup systems. We also looked at wind turbines, dump loads, diversion controllers, and braking. That was important because wind is not the same as solar. When solar charging stops, panels can simply stop producing usable power. But a wind turbine still has moving energy that has to be controlled. That is why dump loads and braking matter. Then we clarified grid-tied, hybrid, and off-grid systems. Grid-tied mainly works with the utility grid. Hybrid can use batteries and may interact with the grid depending on setup. Off-grid is designed to operate without depending on the utility. But off-grid does not mean low voltage only. An off-grid system can still produce normal 120-volt or 120 240-volt AC power. And hybrid does not automatically mean selling power back. Some hybrid systems sell, some do not. Some are zero export. Some are backup only. The words matter because wrong terminology leads to wrong system design. So here is the big lesson from the first 25 weeks. Solar is not about buying parts. Solar is about building a complete electrical system that matches the job. Panels matter. Batteries matter. Wire size matters. Connections matter. Fuses and breakers matter. Charge controllers matter. Inverters matter. Loads matter. System voltage matters. Real-world conditions matter. The beginner question is, will this part work? The better question is, will this whole system work safely under real conditions? That is the mindset we have been building, not guessing, not copying random diagrams, not just throwing parts together. A real system, a safe system, a system that can be understood, repaired, expanded, and improved. That is the foundation, and everything from here forward builds on that.